Hello. Hello and welcome. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is my pleasure to welcome everyone here today. Both those of you here in the live studio audience, but also those of you watching online on either our website or one of the many science communication colleagues' websites around the globe. The lecture itself will last approximately 1 hour and will be followed by a question and answer session. For those of you online, we have Dr. Damien Pope and Dr. Kelly Foyle and a team of PI researchers behind their keyboards in the chat zone ready to engage in online conversation. And they'll be online engaging in conversation for 30 minutes after the lecture as well as during the lecture. So if you want to take part in that conversation, use hashtag #PILive. Also, I'll take a question or two from the Twitter feed at the end. And now, it's my pleasure to introduce tonight's very special guest speaker, Dr. Amanda Peet. Originally from the island nation of Otairo, also known as New Zealand, Dr. Peet earned a BSc at the University of Canterbury and a PhD from Stanford University, and has won both a Radcliffe Fellowship from Harvard University and an Alfred P. Sloan Foundation Research Fellowship. Dr. Peet is currently an Associate Professor of Physics at the University of Toronto and an affiliate of Perimeter Institute. And now, with string theory Legos for black holes, please join me in welcoming Dr. Amanda Peet.
So thank you very much for that very kind introduction. It's a magnificent privilege and pleasure to be here today, so I hope I can give you an interesting set of things to think about. So ever since I was a little kid growing up in Aotearoa, as mentioned, also known as New Zealand, I have looked at the world through the eyes of a scientist. 25 years ago, I took a big leap and moved to America. Didn't know anything about it before I went. But at Stanford, I got really interested in two subjects at the same time. One of them is string theory, and the other one is black holes. And those are objects which can form in our universe when very massive stars literally run out of gas. They run out of gas to continue fusion, and they undergo runaway gravitational collapse. Black holes are really fascinating because they have ultra-strong gravity, and they also pose very deep questions, even today, about how quantum physics, the physics of the microscopic world, and the force of gravity that governs heavy things, how they work together. So my goals for tonight are to explain three things. The basic idea of string theory and why we bother with this idea. Secondly, why we need string theory or some other theory of quantum gravity to investigate interesting questions about black holes. And thirdly, why the toolkit of string theory is so versatile and powerful. Just a small style note, I'll try to keep this humble and accessible, and I'm here tonight in front of all of you in person and online because I dared myself to try to explain this rather abstract theoretical physics to the lay public. So buckle your seatbelts, sit back and relax, and enjoy the ride. If you want to know roughly whereabouts I am in the talk, there's going to be 30 pages. The page numbers are shown up at the top right of the page. And you can see where I'll be along in my talk by following the white dot along the circles at the top. So if you want to know roughly where we are, and if you've fallen asleep and you need to get back the point of the talk, then you can use that little map at the top to find your way around. So the first part, I'll spend about a third of my time talking about what the universe looks like through the eyes of a string theorist. Now, many of you will have a smartphone that might run Android or iOS. Well, I'm looking at the operating system of the universe, which I'll call Universe OS. And what I want to show you is why string theory is a useful tool for doing that. I'll take then about a quarter of my time to talk about Stephen Hawking's information puzzle about black holes and why it raises so many fascinating questions that we're still wrestling with today. And for about the final 40% of the talk, this is the third category up here, I'll show you how to use just the very basics of string theory, and I promise no equations, to build two things that I hope will blow your mind. One is to be able to build string theoretic models of black holes. And secondly, how we can use string theory to show realizations of the idea that the world might be a hologram. And that's the second way I want to blow your mind. And then we'll, roughly speaking, be at the end of the talk, and you can ask me any questions you like. So that's approximately speaking how things are going to go. So, I'm a physicist, and what do physicists do? Well, our basic drive is to find interesting systems in nature, poke them, and to see what happens. And for much of the 20th century, most physicists classified themselves as either experimentalists or theorists. But in the 21st century, physics is really much more like a holy trinity of effort. 3-in-1 oil, giving you a little analogy there. And there are 3 legs of the modern enterprise of physics. 1, you do experiment, you measure the physics in a lab. 2, you do theory, you model the physics with mathematics. And thirdly, and this is the new thing that came in since computers became powerful enough to really help with doing physics, is computation. So I'm not an experimentalist, I'm not a computationalist, I'm a theorist. So I'm a fairly abstract sort of person. But I hope to make my discussion today really accessible, so that's the idea. So string theorists like me want to explain the structure and the origin of elementary particles and forces and even space-time itself, and we want to understand this all the way from tiny subatomic scales out to the very edges of the universe. So in other words, we're daring to seek the operating system of the entire universe at once, not just a killer app that covers, say, condensed matter physics or early universe cosmology. We want something that will work over all those 60 orders of magnitude or so. And if you don't relate to powers of 10, you can think in musical terms, and the dynamic range that's involved in what we're studying would correspond to about 200 octaves of music. And by comparison, the Guinness World Record for the vocal range of a human being is about 10 octaves. So humans are optimized for certain length scales. For example, we can easily deal with millimeters out to kilometers, but if we want to go much smaller or much larger, we need apparatus to help us, like microscopes or telescopes. Examples would include the Large Hadron Collider, which is the most powerful microscope we have on Earth, located near Geneva, or for really big scales, something like a Hubble Space Telescope in orbit. Now, the question about size, it does matter in the case of physics. There is an old science joke, which many of you who like physics may have heard before, it goes like this. Sociology, well, that's just applied psychology. Psychology, well, that's really just applied biology. Biology, well, that's just applied chemistry. And chemistry, well, that's just applied physics. And the joke is meant to make physicists feel very powerful about their status in the universe. But the real moral of the story is the following, that different tools are appropriate to different length scales. If you want to study societies, or mitochondria, or Higgs bosons, you'll need different tools to do those analyses. And if you're interested in building a theory in theoretical physics, this is a little bit wiring up a mixer. All the dials and sliders on your dashboard indicate how strongly the various components, like your things that you plug into your mixer, will interact. And these sliders or dials, physicists have a word for it, they call them couplings. That just indicates how strongly things interact with one another. So, through the eyes of a string theorist, what does the world look like? If I have an apple that might have fallen under gravity, then what happens if I try to ask what lies beneath? So it took me a while to try to make this diagram, so I hope it's kind of understandable. I'm not very good at drawing things on the computer, but I hope it'll give you the idea that inside an apple, if you look really close, zoom in, you'll discover that in there's something like a fructose molecule. And if you zoomed in on one of the carbon atoms and blew that up to something really big, then you would discover that there are these electrons orbiting around a very compact little nucleus in the middle that's positively charged. And so those electrons are considered to be subatomic particles, and inside each proton and neutron, those are actually not elementary, they're composite particles, and they have little things called quarks inside them, and some things called gluons that glue them together into the nucleus. But you can ask the question, if you've got this wonderful view of modern particle physics, what lies beneath that? Is there more layers of the onion to peel off? And what physicists have discovered by looking for various kinds of elementary particles is that there's not just the up and down quark, they have some heavier cousins. The electron also has a little sibling called an electron neutrino. That's something that's emitted when radioactive beta emitters, like cobalt-60, radioactively decay. And the electron and its little sibling have some heavier cousins as well. But you might wonder, and there's also some particles in here that are responsible for messengering forces between subatomic particles, but how do we distinguish between all these different subatomic particles. It looks like a zoo, and it's very difficult to sort of organize the information. So one of the things about physics is that you can ask what things various observers will agree on. So if I'm studying an electron in Montreal or on Mars or on Alpha Centauri, I want there to be a way of distinguishing that that's an electron that doesn't depend on where I am. So the mass of the particle, the rest mass for those of you who are experts, and there's an intrinsic little amount of spin for a particle which you can't remove without changing its identity. And then there are things like charges, for example, the electric charge of an electron. And this little spin can be either an integer, that they're called bosons. That's where the word boson comes in the Higgs boson, which you may have heard about, discovered almost 3 years ago at the Large Hadron Collider. And if spin is a half integer, those are called fermions. And what people have discovered is that the matter, things like the quarks inside protons and neutrons, or the electrons, are made of fermions, while the bosons, the things that have an integer spin, are things that transmit a force. Now, this might sound a bit weird. How can a force be transmitted by subatomic particles? And I'll just give you a really quick analogy. Supposing that this lovely lady in the front row here and I dressed up in electron suits and put on ice skates and went on a freshly Zambonied ice rink. And then I threw a ball to her. The ball is going to be the force-transmitting particle, by the way, give you the punchline. So when I throw the ball, I'm going to recoil backwards. When she catches the ball, she'll recoil backwards. If she throws it to me and we keep throwing it between us, we're going to move further and further apart. And that's the particle physics version of electric repulsion, the same thing that causes your hairs to stick up when you've got static electricity in the winter. So that's all a picture before string theory came into the picture. So when we learn about atoms, molecules, and maybe if we're lucky, subatomic particles in school, we're taught that the fundamental constituents of everything, the Legos that make up the universe, are elementary particles, emphasis on the particles. The key feature of a particle being that it's point-like and it doesn't have any structure to it. But we can ask, string theorists decide to ask a very impertinent question. We say, well, what experimental evidence do you have that electrons and quarks and photons and gluons are actually point-like? Even the Large Hadron Collider, which is humanity's most powerful machine yet, can only reach down to about a length scale called 10 to the minus 20 meters. Now, to give you an idea about how small that is, if you took a meter and blew it up, chopped it up into 1 billion pieces, then you took one of those billion pieces and blew it up into 1 billion pieces, and then took 1% of what was left, that would be how small it would be. So it's really freaking small. If you blew up the Large Hadron Collider distance scale that it can dig down to my size, I would be as big as the Milky Way almost. That's how big that's how powerful that machine is at digging down to short distances. But it still can't go down to infinitely short distances. So string theory, as I said, is a bit of an impertinent idea. It says, well, let's suppose that the Legos of the universe are actually not point particles, but one-dimensional, tiny vibrating strands of energy that we call fundamental strings. Now, these fundamental strings are much smaller than the molecules in the macroscopic kind of string that your cat will play with. You can imagine that these are tiny, tiny little strings, and they're vibrating away. Now, why bother with a Lego that's more complicated, frankly? I mean, why make life difficult for yourself? Why not just stick with particle physics and go all the way to having these strings? And one of the answers is that there are a lot of unexplained patterns and even some puzzles in the standard model of particle physics that we need to have some explanation of, or we would like to understand some of the why questions rather than just the how questions. And the key feature of strings that allow us to do more than particles can, in particular build a theory of quantum gravity, is that strings are versatile. Like a musical instrument, like a cello string you can play or a guitar string that you could pluck, any one string can make a number of different notes. So it'd be like this. You can make different sounds coming from the one string. And the idea is that these strings, tiny little fundamental strings, if they vibrate in different ways corresponding to different subatomic particles, this is a little bit like having different musical notes. And we like to say poetically that string theory is like a symphony of nature. But you can take it a wee bit further than just being poetic. One of the first questions you might have is, how can a string possibly represent a particle? And I want to give you an example. Right here I've got a little closed string, and it's probably fairly difficult to see it, but that's my point. If one of the people in the very back who has gray hair could tell me, can you tell that this is a little loop, or does it just look like a dot? Well, it's going to look roughly like a dot. Some of you might have really good vision, in which case you could resolve the fact that it's actually a string and not a particle. But that's the idea. If you only look at a string with very low resolution, it'll look like a point particle. So strings can do everything particles can do, but they can do more. Okay? So at low resolution, a string really does look just like a particle would. So string theory has two types of strings in it. One of them is open strings, which have ends. You can imagine that if my body is an open string, there are the endpoints doing this. And then there are also closed strings, which look more like rubber bands, and they can be vibrating away, but they don't have any ends to them. And if you do the physics of open and closed strings, you discover something very interesting. If you look at the lowest possible mode of vibration of an open string, the lowest mode of vibration is called the ground state by physicists. That turns out to have 0 mass and spin 1. The really amazing thing is that those are the vital statistics of 3 of the force-carrying particles in the Standard Model. That photons are massless and spin 1. Those are the ones that transmit the electromagnetic force. The gluons that transmits the strong nuclear force that binds quarks inside protons and neutrons. And it has the right mass and spin to describe even the W and Z bosons that transmit the weak nuclear force that powers the nuclear fusion reaction in stars and keeps the sunlight running from our local star, for instance. So open strings manage to describe 3 of the 4 forces of the Standard Model. What if you consider closed strings instead, the ones that don't have any ends? Well, if you do the analysis and write down the equations, you discover that the ground state of a closed string has 0 mass also, and it has spin 2. And that is the vital statistics of the hypothesized graviton particles that transmit the gravitational force. So string theory, just by having open and closed strings which can interact with one another, you can even have 2 open strings that can join up and make a closed string, it naturally includes both the gravity particle, over here, the graviton, which is not included in the Standard Model of particle physics, and then the other, the photon, the gluon, and the W's and Z's. String theory manages to unify the forces together in the way that particle theory could not. Einstein, by the way, dreamed of unifying electromagnetism and gravity together. He didn't focus very much on the nuclear forces, but unfortunately he didn't live to see this unification of forces that string theory provides. Maybe he would have enjoyed it. Can't say, of course. So, string theory does more than just unifying the forces. It does a few other things as well, and I'll just mention 2 of them on this slide. First, I'll just mention that we talked about the ground state of the string. That corresponds to the lowest possible frequency produced by the vibration in an analog of an organ pipe or a cello string. But you can make excited states of the string, and those would correspond to higher harmonics of the musical instrument, and they would represent, in the particle physics language, interacting particles with higher mass and higher spin than the ground states that we already talked about. So, but you know, the most amazing and mind-blowing thing that students of string theory discover when they dig into it is that when you work out the quantum theory of strings, you discover that gravity pops out for free. Now, this doesn't impress most modern humans, because gravity was actually discovered centuries before string theory was. So having predicted it after the fact, people aren't very excited about that. However, had string theory been invented first, it would be famous for having correctly predicted the existence of gravity, and its inventors would probably have Nobel Prizes. But, you know, too bad, history turned out the other way. I haven't got very much time to say much about this, but string theory also predicts extra dimensions of space. If anybody wants to know a bit more about that, I can mention that in the Q&A session. But these extra dimensions, because we don't see them, like I can only see left and right, up and down, back and forth, those 3 dimensions and the dimension of time. So these extra dimensions of space that string theory predicts are tightly curled up and hidden from view. But the thing about strings is they're extended objects, and they can actually wrap around some of these extra dimensions that are tightly curled up. And this has very profound consequences for changing our expectations about what happens with space-time when we're doing quantum physics. So you can think of string theory as a fairly complicated enterprise. Learning it is a bit like as difficult as learning to become a high-end Swiss watchmaker. It has a lot of complicated moving parts, and you have to fit it into pretty tiny dimensions. But string theory, superstring theory is capable of describing all the subatomic particles in the Standard Model, plus gravity, plus possible zoos of yet undiscovered particles as well. It even unifies forces together with matter, the fermions and the bosons, and can even describe the emergence of space-time itself. So what we've seen is, if you like, a little bit of an evolution of the periodic table over the years. We used to think that it was all, structure was all about atoms and those made up molecules. But then we discover when we dug deeper that there's the Standard Model of particle physics with the quarks and the electron and its friends, and force-carrying particles, and the Higgs boson, which was the last element of the puzzle that had been predicted but not discovered until a few years ago. And the idea is once we've looked at the string theory picture, then you're looking at the story of string theory geometry, which replaces the periodic table. By the way, various of you may know that hydrogen, one of the elements that's important for organic life, was created in the Big Bang, but carbon, nitrogen, oxygen, phosphorus, sulfur, the other elements that are important for life, were created in stars from nuclear fusion, and the more complicated ones from supernova explosions. So literally, we are made of star stuff, every one of us. We are connected with the universe that way. And if some of you is wearing a gold wedding ring, for example, these were created in supernova explosions. So the fact that you have any gold at all is because of that happened in the universe. Pretty cool, huh? The universe is a pretty neat place. Now, string theory allows you to do something that particle theory doesn't, which is to build a better theory of gravity than what we already have. And I want to emphasize that although I've said the string theory picture gives a bit of a refinement of the picture that we already understood before string theory was really in the picture, you might wonder if everything you learned in high school is wrong. Well, no, it isn't. It's just been upgraded, a little bit like going from iOS 5 to iOS 6 or iOS 7 and better versions of the operating system. The better versions, the later versions can do all the things the earlier ones could do, but they can do more. So Newton was the first guy to build a theory of gravity. He built what I like to call gravity 1.0. And for him, gravity was a force that was transmitted instantaneously across space. And the key feature of Newton's theory, which was so amazing at the time, is that unified the gravity from the terrestrial, like the physics of baseballs when thrown up in the air, and the celestial, the motions of planets and moons and so forth. So Newton's equations, while they're the least sophisticated theory of gravity available, they were good enough to send men to the moon. So, pretty good equations. Then Einstein came along almost a century ago and built gravity 2.0, which he called general relativity, or GR for short. Run out of space on the page sometimes, so I write GR instead of general relativity to save space. So for Einstein, instead of gravity being some mysterious force that was instantaneously transmitted, for Einstein, gravity became the geometry of the smooth fabric of space-time. And the key feature of Einstein's theory is he baked causality into it, the fact that nothing could go faster than light. For example, if I press a trigger and then a bomb goes off, pressing the trigger caused the bomb to go off, then the bomb going off didn't cause the trigger being pressed. There's a sense of which caused what in the universe. And Einstein was very keen to make that work. So general relativity, gravity 2.0, didn't throw Newton's theory out of the universe. It didn't kick it out of the water. It said, well, actually, I'm going to stand on your shoulders. I'm going to see further because I'm standing on the shoulders of giants, is a particular quote from Newton. He was actually, by the way, that was a snarky comment at one of his rivals, Hooke, who is relatively short. Yeah, people are just human through the centuries, even the most famous physicists, we're still humans. But so GR was better than Newton's in the sense that it could handle describing more experiments. But if you got back to the regime where Newton's equations were valid in the first place, low speeds and weak gravity, then you got back Newton's theory. So that's the sense in which Einstein's theory supersedes Newton's. And what we're looking for right now, string theorists among us, is to build gravity 3.0, a better theory of gravity than Einstein's that will be able to handle quantum gravity situations. And maybe the different possible pathways to quantum gravity that rival approaches are investigating, they actually may end up converging in the end, or we may end up getting different answers, in which case we'll have to figure out which one is right. But I'm betting on string theory, and string theory says that gravity is just the lowest vibration mode of closed strings. That's really all that string theory says about the nature of gravity. There's lots of complicated consequences, but that's a basic idea. And the string toolbox has been really fruitful in about the last couple of decades, which is one of the reasons why I'm using it. So it's a strategic choice. It's not that I think that string theory is the one religion that should be obeyed, and if you don't believe it, then you're somehow inferior. Not at all. It's just because it's the best toolbox that's out there to study the kinds of questions that I'm interested in answering. So you might wonder, all this geometry and all this extra dimensions and all this mathematics might seem too mathy. But there's a reason why mathematics is the language of theoretical physics, and that is that math has proven itself as an unreasonably effective way of working with the laws of nature. So math influences our standards of what we consider beautiful in physics, but it's not the final arbiter. The arbiter of what constitutes a useful physical theory is, does it help you describe the natural world? And if theoretical physicists, another interesting point to make is that when theoretical physicists are studying interesting phenomena, we prefer to be able to calculate something, like work out some consequences and be able to test them, rather than just sort of daydreaming about a topic and hoping that we'll be able to make a theory of quantum gravity without doing any calculations. So we like to have a model, even if it's not fully accurate or realistic. So this is one of the metaphors of my talk, that you can think about the natural world as a bit like the real blue jay, and the models that I'll be using to build black holes and holograms for you are a bit like the Lego blue jay. It looks a lot like the blue jay. It has many of the features. It gets right a number of the aspects, but Lego birds can't fly and they can't do some other important things. So we've got a ways to go to make our Lego models more realistic. But I like to use string theory for answering quantum gravity questions because I think it has the best ratio of features to bugs. String theory has some bugs, some drawbacks, and it has some benefits. And what I'm trying to tell you about tonight is some of those benefits so that you can figure out for yourself whether or not you think this is interesting. But I hope you'll agree with me by the time I finish that it is. So let me now switch gears into discussing Hawking's black hole information puzzle. Sorry, I couldn't resist when I found the image. You know, it was too easy. But OK, so if you launch a satellite that's around Earth just right, Earth's gravity will balance perfectly against speed and inertia. If it was too slow, it would fall back to Earth, and if it was too fast, it would escape and fling off into outer space. Now, black holes have such strong gravity that inside a certain radius from their center, nothing can escape, not even light. And that's why it's called a black hole. And this surface of doom, inside which you mustn't fall, is called the event horizon. If you do get too close and fall inside, you can never escape, no matter how strong the rockets are that you've strapped to your feet. Vroom! You still can't get out. So an object is called a black hole if it's dense enough to be contained within its own event horizon. Now, Earth actually, you might wonder, is Earth a black hole? And the answer is no. If Earth were to be a black hole, it would have to fit all of it, including us and all the rocks and everything in it, inside about the size of a ping pong ball. So that gives you an idea about just how compact a black hole is. It's really, really compressed compared to our world. Now, if you happen to replace our sun by a black hole of the same mass, our orbit wouldn't change. But we wouldn't be getting any sunlight or any warmth, and so we'd all die. So that would be fairly catastrophic, but not because we fell into the black hole. The key is, if you don't get too close, you won't fall in. But if you do fall in, then there's a really big problem there. The heart of a black hole is a place called the singularity, where the curvature of space-time becomes infinite. Even the nuclear forces, which are strong, they're strong enough to, help us make nuclear bombs, even those forces aren't strong enough to resist matter being shredded into its fundamental constituents. And incidentally, if you have a small enough black hole, an astronaut unlucky enough to be approaching near one, it would even get shredded before they cross the event horizon. So black holes are pretty violent places. And the singularity at the heart of the black hole, I'd like to argue, signals a serious internal problem with Einstein's theory of general relativity. His equations, which are supposed to predict the physics, they fall flat on their face at the singularity. They can't predict anything, there. If you ask them the question, what's the curvature of space-time? It says infinity. If you ask it, what are the tidal forces on a person? Infinity. What's the probability of creating an electron? Infinity. And you get the idea that the theory is just a little bit sick. So this is why we need a theory of quantum gravity, string theory or whatever other approach you please to try to analyze these questions. So Stephen Hawking, he's a really, really smart guy, and I was lucky enough to meet him as a graduate student. So that's why the picture I have of him on this thing is actually from when he could still use his hand to run the machine. Now he has a little eye recognition thingy that he uses to be able to communicate. At any rate, he went really for the jugular in his research on black holes. Now, black holes, there's a very limited amount of information that you can know about from the outside. In fact, there's only 3 things. You're allowed to know the mass, the spin, and charge, if it has any. Those are the same labels, by the way, that we use to classify subatomic particles. But for a black hole, you remain ignorant of everything behind the horizon. Now, Hawking, in investigating this, proved something very surprising 40 years ago by combining tools of general relativity, Einstein's theory, with quantum mechanics, and he proved that black holes emit radiation. And this Hawking temperature is kind of stupid. It only knows about the mass and the spin of the black hole and the charges if it's got any. Now, for real-world astrophysical black holes, the Hawking temperature is actually really cold, colder than the cosmic microwave background radiation left over from the Big Bang. So it doesn't really matter in real life, but it still matters in principle. And let me show you the following thought experiment. Let's suppose that you threw a 1 kilogram book into a black hole. After it had disappeared behind the horizon, what you would be seeing coming out of the black hole would be this weak Hawking radiation. Now, instead, suppose that you did an experiment where you threw a 1 kilogram fish into the black hole, like an orange roughy from the waters off New Zealand. Then you would get exactly the same radiation out of the black hole. So the Hawking radiation knows nothing about the difference between books and fishes. It just knows the mass, and the mass is the same, kilogram, kilogram. So Hawking realized that this had really profound implications, that black holes in general relativity lose information. This is very upsetting for a physicist. Okay. But there's an interesting consequence of the fact that black holes have a temperature. They radiate like a thermal system. And there was, in the 19th century, physicists invented some tools called thermodynamics, that basically means things that change with time and are thermal, to try to figure out how to help build more efficient engines. And the tool set lets you describe the story of a very large number of molecules. For example, in the gas in this room, there are bazillions of molecules here, and it would be pretty difficult to follow the motions of all of those individually. But thermodynamics lets you describe it just in terms of a few gross properties, like the temperature, or the pressure, like the pressure in your car tire, or the energy density. And thermal physicists discovered something important called the entropy. And it's usually denoted by S in formulas. That's not especially important. We're going to write a formula for it on the next page. That entropy encodes the amount of energy that's wasted as heat in a thermodynamic process. Alternatively, you can think of it as encoding the degree of disorder of a physical system. So if you have a teenager and they have a very tidy bedroom, that would be a low entropy situation. But if all the clothes were scattered all over the place and everything was a terrible mess, that would be a high entropy situation. If you want to think alternatively in terms of water molecules, ice, which has very specific patterns, it's a more ordered system, that has lower entropy than water, which is all sort of spread out and disorganized because the molecules can move around. So why is this important? Well, when people studied black holes, people like Hawking, but also others like Jacob Bekenstein, they learned that black holes obey the laws of thermodynamics. And in particular, the second law that says the entropy of a system doesn't spontaneously decrease with time. There's no such thing as a perpetual motion machine. There's no such thing as a free lunch. Bummer. Okay, but thermodynamic people discovered something else when they were doing these investigations. And one of them, Ludwig Boltzmann, thought about the fact that if you have a gas, if you know the quantum physics of just one molecule of gas, like you know the detailed microscopic physics of that system, you can actually derive all the thermodynamic properties. And he discovered a formula for the entropy, generally, the thermodynamic entropy, that energy that was wasted as heat, in terms of the number of ways you can configure the system. This is one of the only 3 formulas that I'm going to be showing in my talk. He was so impressed with his derivation that he had it inscribed on his tombstone. I hope that I don't put a quarter of a black hole that's named after me on my tombstone. Yeah, yikes. At any rate, a century later, about 40 years ago, Jacob Bekenstein and Stephen Hawking found the thermodynamic formula for the entropy of a black hole. And all I want you to focus on is the fact that it's proportional to the area of the event horizon. It's got some other stuff in it, like Boltzmann's constant, the speed of light, the strength of gravity, and h-bar, which is a constant that tells us about quantum mechanics. But this black hole entropy encodes our ignorance about what lies behind the horizon. We don't know what's behind it. We're only allowed to know the mass and the spin. So there's a lot we don't know, and that's what the entropy encodes. Now, researchers like me want to explain this entropy of black holes starting from first principles. We want to use a quantum theory of gravity and explain where that entropy comes from. And to do that, we're going to need a theory of quantum gravity. So what is the problem if you just try to use Einstein's theory to do black hole physics? Well, the problem is that the fundamental ingredients, Einstein's general relativity and quantum mechanics, turn out to be allergic to each other, like warring marriage partners that can't stand to be under the same roof. And how does this arise? Well, general relativity, which was born about a century ago, is a very well-tested theoretical description of heavy things, things like planets, stars, galaxies, and even the whole cosmos. Whereas quantum mechanics, born slightly later, is an exquisitely well-tested theoretical description of very small things, things like molecules and atoms and quarks. Now, both general relativity and quantum mechanics have nearly a century's worth of data backing them up. But unfortunately, they're fundamentally incompatible. The real reason is that general relativity is all about the smooth fabric of space-time, so it's a kind of chill concept, whereas quantum mechanics has a random jumpiness built into it. And this isn't just a minor problem, it's a fairly major theoretical emergency. A little bit like the situation of having roads that were governed by incompatible traffic rules. So it's a bit like general relativity says, keep left, and quantum mechanics says, keep right. And then the question is, do we ever have situations where these overlap, in which case we'd have carnage, dead bodies everywhere. So can we just sweep this problem under the rug? Can't we just say, well, general relativity, you can stick to governing heavy things, and quantum mechanics, you can stick to governing small things, and we'll pretend that those Venn diagrams of heavy things and small things never overlap. Can't we just sweep it under the rug? And the answer is no, because there might be physical systems that are both heavy and small, in which case we would have to apply the rules of gravity and quantum mechanics at the same time. So we need to have a theory of quantum gravity to be able to explain those very extreme physical systems. And there are 2 places where this happens. One is in a black hole. Wonderful. The rest of my talk is about black holes. And the second one is at the Big Bang, when the universe itself was super tiny and there was a lot of stuff in it. So that's why we need a theory of quantum gravity. So why is string theory the superior tool to use in this context? Well, that's because it manages, just by positing that the Legos of the universe are strings and not particles, it manages to fix this war between quantum mechanics and general relativity. It's like string theory is a bigger tent that says, hey, you can both come under my tent, it's okay, we can have both quantum mechanics and general relativity, but because my tent is bigger, we'll manage to let you work together under the same roof. So what are some of the major features of quantum theory? I've mentioned just a little bit about general relativity. Energy only comes in discrete lumps, they're called quanta. Everything, including electrons and protons, has wave-like behavior, and that can give rise to phenomena like interference. And if you have a particle that has a quantum wavelength, the faster it goes, the shorter its wavelength is. So that's one of the ideas that we use in building an electron microscope. If we want to dig down and see the structure of something like even as much as DNA, we can accelerate the electrons faster so they have a smaller wavelength so we can resolve shorter distance things in nature. And the third thing about quantum mechanics that's new and weird to somebody who's only dealt with the physics of dogs and baseballs and planets and cars is that physics at the microscopic level has a randomness to it, a jumpiness to it. And this changed fundamentally the way physicists think about determinism. Physicists wouldn't be able to predict what an actual event is going to happen, but we can tell you the probability that it's going to happen. So that changed a little bit the way we think about physics. So the main symptom of general relativity sickness of a quantum theory is that if you look at very short distances or use very high energies, then the probability of scattering of gravitons, the particles that transmit the gravity force, grows to be above 100%. And those of you who have studied anything about probability know that it has to be in between 0% and 100%. It can't be like 297%. So clearly what's going on with general relativity and quantum mechanics is some big problem. So as we said, if you just posit instead that the Legos of the universe are strings, then if you choose quantum mechanics as the more fundamental thing of these two, you say to yourself, I'm going to do the quantum mechanics of strings, and out pops general relativity. So that's how we manage to have both of those warring factions under the same roof. And the essence of how string theory heals the sickness of general relativity is that while particles are pointy and kind of hard and singular, strings are extended and softer objects, and they interact by smoothly splitting or joining in a more spread out way than particles do. And this is the crux of how string theory heals this problem with Einstein's theory of gravity. All right, so I've done all the introducing, that we've motivated why string theory is cool and why we need it to study black holes. And now I'd like, with the remaining part of my talk, to try to blow your minds a couple of times. But to do this, I want to assure you that I'm going to dial back in the complexity right now. We're going to get really super basic. Just talk about strings and a few extra things, but that's going to be it. Nothing complicated. So if you want to, just mentally do a bit of a stretch and breathe as we go into the next part. Buckle your seatbelts. Okay, so we've already met the two basic types of strings. There are open strings and closed strings. Or in my little Lego terms, that's an open string and that's a closed string. Now, strings have a tension to them, like you can tune a piano by changing the tension of the piano wire, and that sets the energy scale of the oscillations, or equivalently the pitch in music. If you make the string vibrate more, you make it vibrate more furiously, naturally that would cost more energy. Another basic aspect of string theory is that it has a parameter that's called the coupling. And this is denoted by GS when string theorists write it down in an equation. And what I want you to think about this number as is it controls the interaction strength between strings. So on your dial, if you turned the coupling down really low, then strings would just mostly mosey around, not interacting with one another. It would be a fairly boring universe. But if you turned it up a lot, then things could feel forces between them and bang into each other more often, and life would be more interesting. So this coupling strength controls, in quantum mechanics, the probability that one string mosey along will just spontaneously emit another string. But that's a bit of a higher degree of complication. The essential thing to know about the string coupling, which tells you how strongly the strings interact, is that string theorists are best at doing calculations when this number is small, because then the probability of just weird stuff happening is pretty low, and we can mostly use simple approximations to describe the physics. This is called perturbation theory. If you happen to be really masochistic, you could turn up the coupling and make it really big, and that would involve opening up the 11th dimension of M theory. But I don't have time to discuss any of that. So if you want to know about that, you're going to have to ask it in the Q&A. All right, but these are the strings. There are open strings and closed strings, and there's a coupling strength. That's all we need to know. Now, in string theory, in 1995, it was realized that there are actually more than just strings in string theory. Turns out there are extended objects, things that could, for example, if there was a brane extending in this direction, it could extend all the way out that way and all the way out that way. And these extended objects come in different dimensions, and we sort of ran out for words for them, so we call them branes, which is just short for membranes. You can think about the surface of a membrane as being a bit like the surface of a trampoline, that if you poked it, it would push back at you. That's called the tension of the brane. And how hard it pushes back at you tells you something about how the brane is likely to fluctuate. So zero-dimensional branes are called particles, one-dimensional branes are called strings, and the higher dimensional ones are like, bigger dimensional trampolines. Now, the key thing about branes, that they arise in string theory as places where the open strings end. So if you've got an open string, you can imagine that this is an open string that has a couple of little endpoints, then the brane is just known as the location where the open strings end. That's it. And it turns out that this is enough to characterize the dynamics of branes entirely, just starting from what we know about strings. You don't require any extra input. You don't have to sort of throw in arbitrary extra stuff to be able to see the physics of branes along with the physics of strings. And if you measure the tension of a brane in string units, you discover that it scales inversely with the coupling. That might sound sophisticated, but all it means is when that coupling dial is turned down to weak, so that we can do our calculations, then the branes are relatively heavy. If you turned the coupling up, they would become lighter. And so if you had a limited energy budget, the branes would be doing some fluctuating as well as the strings. So okay, so far we have string coupling from the last page, and from this page we've got branes. And we can put these together now to find out how to build spacetimes, things that correspond to warping of spacetime, things like black holes, which contain very strong warping of spacetime. We can even build these using the branes of string theory. Just stay with me for the moment. I know it sounds a bit unlikely, but follow this simple argument on this page and we'll see how that works. So let me consider a system made up of a whole stack of branes piled on top of one another. They're actually all on top of one another, but I separated them a little bit so that you could see them on the piece of paper. Also, I'm kind of bad at drawing. So the question we can ask is, how much do these branes warp the fabric of spacetime? And the answer will obviously depend on how close we are to the branes, because if they're heavy, then they're going to warp spacetime, and if we're closer up, that warping would be stronger than if we were further away and the effect of the warping wasn't so dramatic. So it depends on that. But the thing that's really interesting about the physics of branes is that how much they warp the fabric of space is proportional to a number. And this number is two things multiplied together. It's the string coupling, GS, that thing on the dial that told us how strong our string interactions were, and it's also proportional to n, which is the number of branes we had in the first place. So if there were 49 of them, you would put 49 in here. This is a little bit like having a multiplicative sound mixer, by the way, if you happen to be interested in that kind of thing. So we said that on the last page, if we wanted to keep our string calculations under control, we need to keep the coupling small so we can cope with working out the equations of string theory. But you can see that if we want a sizable warping of the fabric of spacetime to try to build black holes, we're going to need to have a large coupling times the number of branes. All right, so here's the trick. If we want this number GS times n to be noticeable, and GS has to be small, then we can have our cake and eat it as long as the number n is very large. So say we had GS was 1/100th, and n was 100, then the product would be 1, which would be a sizable amount of warping. So the message to take away from this is that if we want to start from very basic string theory ingredients, the microscopic Legos of the universe, then we can actually build big fat spacetimes like black holes. All we need is to use a large number of branes. Okay? So this was a relatively simple argument. It just said that the warping is proportional to the coupling times the number of branes. We wanted the coupling to be small, so we needed the number of branes to be large. Okay. So that's one of the things we need to know about branes to build some models of black holes. So let me just show you a little bit how it works with Legos. And this is where the pictures really help. So if you're a first-year graduate student working with me at the University of Toronto, you can very easily calculate the forces between branes that have different dimensions to them. And what you find is a few things. One of the things you find is that branes that have the same dimension, that are parallel to one another, don't feel any forces, they don't feel attraction, and they don't feel repulsion. It's just neutral. They're like, okay, you can be here, I don't care. Nothing special happening. Another no-force combination you turn out to be able to have is something, a brane that has 5 dimensions, and since it's very hard to think in our minds about what 5 dimensions might look like, I want you to think of the 5 branes as the yellow Legos. So they have quite a few dimensions and they're kind of big. But if you put a 1 brane, where one of the directions of the 1 brane is pointing along the direction of the 5 brane, that's a no-force condition as well. And this is handy if you want to try to build black holes, because 1 branes and 5 branes have different kinds of charges as well as carrying mass. So I'm currently cooking a recipe, and so far I've identified that I'm going to use some yellow guys, the 5 branes, along with some 1 branes, which are the red guys. Is everybody able to tell the difference between colors in the room? Does anyone happen to be colorblind? Okay, cool. So that means the color analogies will work. All right, so we've got 1 branes and 5 branes. And it turns out you can add to this mixture without upsetting the no-force balance. You can add things called open strings, and they have some momentum. All that means is that they're racing along the direction of the red guy. And if you have these little purple fellas, they don't feel any force with the red fellas. Also, these little open strings that carry momentum don't feel any force from the 5 branes, the yellow guys. So the terminology aside, what we've got is some red guys, these fellas, and the red guys and the yellow guys don't feel any force between them. We learned that on the last page. The red guys and the purple guys don't feel a force, and the purple guys and the yellow guys don't feel a force. So if all of the 3 partners don't feel forces between them, we can safely combine them together without messing up that no-force condition. So these are some of the ingredients that we need to be able to build a black hole. And this is supposed to be my Lego analogy for a black hole that carries the momentum, the purple fellas, and the 1 brane charge, the red fellas, and the 5 brane charge, which is carried by the yellow guys. Now, black holes are compact objects. They're not extended like branes. So if we want to make a black hole, we actually have to wrap up any of the extended directions, the branes, on the small rolled up dimensions of space. And I won't go through the details, but what you start from with building the story with the branes is 10 dimensions of space-time. That's what superstring theory predicts. And then if you roll up the 5 branes and the 1 branes, you roll it up on 5 dimensions. So 10 minus 5 leaves 5 dimensions left over, and that's the kind of black hole that we can build for you. Now, I'm really bad at drawing, so this is supposed to be a picture of a little black hole. And the black hole has purple charge on it, and it has red charge on it, and it has yellow charge on it. And once you've found this black hole that carries mass and these 3 different kinds of charges on it, this was constructed by 2 people at Harvard in 1996. And here's the punchline. If anybody beside you has fallen asleep listening to all these boring details about strings and branes, poke them in the ribs to wake them up, because this is where the punchline is coming along. And so why was all the stuff about 1 branes and 5 branes and momentum so important? And the reason was that these guys, when they made this black hole out of the strings and branes, they were able to calculate, knowing what we know about the physics of 1 branes and 5 branes and momentum, to actually calculate from first principle, starting from string quantum mechanics, to calculate using the Boltzmann formula what the entropy of that system would be. And it turned out to give exactly the same answer as the Bekenstein-Hawking entropy predicted 40 years earlier. So this was really important for the string theory community because people had managed to use this really abstract theory of quantum gravity to do something useful, at least to a physicist, which is to calculate that, find that holy grail, to calculate that entropy of the black hole. That Bekenstein and Hawking had found that formula for the thermodynamic entropy decades ago, but they hadn't been able to explain where it came from. Why is the formula what it is? And what string theory has been able to do is to calculate the entropy. You get exactly a number, 2 pi times the square root of the purple charge times the red charge times the yellow charge. And it was pretty amazing that we were able to do that for these black holes. So people have even been able to take it further and come up with string theory models of Hawking radiation. That story that we learned earlier, that black holes emit radiation. And I just want to take a couple of minutes to tell you how that happens. Our system was made from 5 branes and 1 branes and strings with momentum. You can sprinkle in a few open strings with momentum that point in the wrong direction, and that turns on a finite temperature without appreciably disturbing the setup of the system. And what happens is if you have some open strings which are pointing in different directions, if they're lucky, they might meet, have a kiss, and become a closed string, and go off into the space-time and get emitted as Hawking radiation particles. And the thing that was really stunning for people like me is if you looked at these escaped closed strings that had joined up and, left the brane and said, bye-bye, we're leaving, then you discovered that although these were created according to the rules of string mechanics, which is really different than the tool set that Hawking used 40 years ago, you get the same spectrum of radiation emitted. And this even works for spinning black holes, and you can do it in 4 dimensions as well as 5, and people were pretty excited that string theory was able to do this, to explain the origin of that black hole entropy, and even to see how Hawking radiation came about, but to have a chance of being able to explain what happens to the information that falls into a black hole because you know how to deal with string theory ingredients. So this is a pretty massive kind of accomplishment, and there's a lot of work that's been done since then developing aspects of that, and that's one of the branches of my research. So this was my attempt to try to describe for you why string theory is useful for building models of black holes. Now, the kicker is that astrophysical black holes, ones that are out there in the universe, don't actually have these purple, yellow, and red charges that I'm talking about. So this is the sense in which string theory is still a Lego set at the moment. We're not able to explain the fundamental origin of the entropy of all black holes, including the astrophysical ones. We've got part of the way there, but we haven't attained a full level of realism yet. But because there was so much progress for these specific cases and these really spectacular agreements that were so important that people realized string theory was something maybe they should hire some string theorists, and it's probably not unrelated that I was hired at the University of Toronto in 2000, not too many years after these developments got a lot of play in the physics community. So let me just try to blow your brain in another way in the last few minutes, talking about the idea that the world might be a hologram. Now, you have met holograms before. You've probably seen one at a science museum, or if you've looked at your credit card lately, you've seen that they have holograms in them. And holograms are fascinating because you can encode 3-dimensional information in a 2-dimensional image. And so the idea that the world might be a hologram is something that occurred to various people, but it wasn't until 1997 when Juan Maldacena discovered the first working model of this idea. And it was a seriously important contribution to theoretical physics, this notion. So let me tell you just a tiny bit about how this came about. So this story of having the idea that the world might be a hologram was obtained by staring very hard at a bunch of 3 branes. Not 1 branes and 5 branes this time, but 3 branes, which are drawn as green Legos. Okay. So you can imagine that we've just got a stack of green Legos, and they're all piled on top of one another, and we're going to stare really hard at it and get kind of a bit tipsy and try to see if we can figure out dreaming something about the system of 3 branes. This is how the holography idea came about. So Maldacena thought, well, let's look at what is fluctuating in our system. We have open strings that end on our pre-branes, but we have closed strings that are moseying around in the bulk, in the full 10 dimensions of space-time. And if you look very carefully at the physics of the open strings that end on the branes, you discovered that the low-res approximation to this physics is called a gauge theory. And because the brane has 3 dimensions of space, it's a 3-brane, and 1 dimension of time, so that's 3 plus 1, that gauge theory lives in 4 dimensions. You can also look at the physics of the closed strings and ask what is the shape of the fabric of space-time. But in general, those low-res approximations are very difficult to believe because string theory is not just the physics of the lowest modes of vibration. It includes all of the tower of possible excitations, the higher harmonics, the higher octaves of musical notes, and it contains quantum corrections, so it's really quite an unholy mess. So generally, the idea of staring at a bunch of 3 branes probably wasn't very a smart one. But you see, then Maldacena came along, and he invented a very clever idea, which was to take a special limit of this system. And this limit he called the decoupling limit, because it turns off interactions between the open strings that end on the branes and the closed strings that live in the bulk. And it might not seem like this is a very interesting limit to study a bunch of three branes from, but bear with me just for a couple of minutes. Because if you turn off the interactions between the closed strings and the open strings, this can create something very beautiful. It was a very stunning insight about physics. So if you have the open string physics on the branes, it turns out that in this decoupling limit, it is exactly the low energy limit. And the physics in 4 dimensions simplifies to just a gauge theory. This is something that we already know how to do in theoretical physics. And this theory turns out to be called a conformal field theory, or a CFT, because it has tons of symmetries. So the open string physics is described by a CFT. If you're interested in the closed string physics, the things that would have to do with the warping of space-time, Maldasena's very clever limit zooms in on the space-time very near to the position of the three branes. And the geometry that pops out is called 5-dimensional anti-de Sitter space times a 5-sphere. The sphere is not very important for our purposes, so you can ignore it. We can focus on this 5-dimensional anti-de Sitter space, which has closed strings and therefore gravity. So in fact, the physics that you get in Maldasena's very special tipsy limit of three branes, you discover that this is called anti-de Sitter space, and it lives in 5 dimensions. Now here comes the punchline. Maldasena said, if I've got open strings and their physics is a CFT, and I've got closed strings and their physics is 5D ADS, well, it was the same set of three branes in the first place. So the physics of these two systems should be the same. The physics of the CFT, which lives in 4 dimensions, should be equal to the physics of the 5-dimensional anti-de Sitter space. And this is the sense in which we have a holographic theory that if you want to describe quantum gravity living in 5-dimensional anti-de Sitter space, you can do it in terms of the 4-dimensional conformal field theory. So the 5D quantum gravity in anti-de Sitter space is like the hologram on your credit card that looks higher dimensional. And the 4-dimensional conformal field theory plays the role of the surface of the credit card. So I know this sounds kind of abstract, but it provides actually the world's first working model of how this works, and it has had some very powerful consequences. And by the way, it even works if you heat the system up to finite temperature. If you heat up the system of open strings that live on the branes in the gauge theory, it turns out to having a black hole in anti-de Sitter space. So holography allows you to access certain questions about black hole physics this way. So I think I've probably blown your minds apart into lots of little pieces by now, but I want to just recap what we spent the last hour doing. For the first part, I gave you a tour of what the structure of force and matter looks like from the perspective of a string theorist. And it really is just the idea that the Legos aren't point particles, they're strings. And strings let you unify forces and do other things like unify matter and force together. And then we talked about some aspects of why black holes are confusing, in particular, how you explain that entropy of a black hole. And then I talked about some string theory ways of building models of black holes and of holograms, just to give you an idea of how far we can go with this kind of physics. And in particular, that we were able to compute the entropy of certain black holes, just for some and not all of them, so partial progress. And we're also able to come up with working examples of this crazy idea that the world might be a hologram. So thank you for bearing with me through all of this jungle of information. And I'm really open to questions, whether they're very technical or very, very basic. So thank you for your attention.
Terrific. Well, let's go to our first question here at the microphone. Oh, you look good under the light.
So, wouldn't it be also possible to make a 4-dimensional thing, a 4-dimensional hologram in 3-dimensional space, by doing the exact opposite? Like,
Oh.
instead of having the analogy being that the thing is true, like the hologram is of a lower dimension,
Yes.
that it runs the opposite.
Well, it's a really interesting question. I'm not certain if I know fully how to answer it, but you did ask a question.
If 3 dimension
Is our universe?
is our CFT, and we're looking at the anti-something another.
Anti-de Sitter, yep, ADS, whatever it's called. And you're asking whether the ADS has to be bigger dimensional than the CFT, or can it be the other way around?
You're in the same dimension as the CFT, and so wouldn't you be able to...
Move to the mic.
If you can move to the microphone, it's easier to hear you. Thank you. I'm a bit old and I can't hear very well.
4-dimensional thing being in 3 dimensions.
Yeah, so we can, the model I built for you said that the CFT lived in 4 dimensions and the anti-de Sitter lived in 5 dimensions.
Shifting it lower.
Yeah, we can shift it lower and we can even shift it higher. String theorists have managed to find 3D CFT is equal to a 4-dimensional anti-de Sitter, and even a 2D CFT was equal to a 3-dimensional anti-de Sitter. And we can even build you 6-dimensional CFT equals 7-dimensional anti-de Sitter. We can't do it in arbitrary situations. We're not that muscular. But you're absolutely right. We can do it in lower dimensions, in particular that we can have a 3D CFT equal to 40 ADS. So you're absolutely right.
Would we see it as a 4-dimensional object?
Well, that raises the question of whether we're even capable of seeing a 4-dimensional object. I mean, I don't know about you, but my eyeballs are suitable for 3D.
Would it be like, to us, would it be kind of like a hologram, or would it be the other way around?
Well, the way I like to think about what higher dimensions would feel like is to explain what a lower dimensional object would look like to us. So if you're interested in what we would look like to a higher dimensional being...
I do have another one after this.
Sorry?
And I do have another one for after this.
You have another question?
Yeah.
Okay, would you like to take turns with some of the other people maybe, if you want to join behind the other 2 people, and that way you can come back and ask another question?
Yeah, why don't I take one? I'll go to the online question, and then we can do some more in-house, and then we can come back. And if she doesn't have time to get to you, we'll get you after the lecture too. Thanks very much. That was a great question. All right, let's go online.
Very sophisticated.
So I have 2 questions actually from Twitter, and they're similar, from Stu76 and SM-. And it's essentially any predictions or comments on how and when string theory might be able to be proven experimentally.
Right. So is string theory falsifiable is the question that people often ask. Is it science at all, or is it just sort of mathematical stuff, fiddling around on the head, angels fiddling around on the head of a pin or something? And the question goes to the heart of what it takes to prove a theory. And we don't really postulate a theory and then set about proving it. We try to say, well, this is the experiments, and can our theory explain those things that we can see, and can it predict new things that we haven't measured yet? So the assumptions of string theory are absolutely falsifiable. There are experiments that can be done, and this is published work that's been around for almost 10 years now, that you could do experiments in nature, in a lab, without having to invent equipment that you haven't invented yet, that would test whether or not the assumptions of string theory are true or false. And so far, none of those experiments has thrown a red flag that says string theory is wrong. Now, it could happen tomorrow. All science is tentative, so whatever we think we know today could be overturned by superior ideas tomorrow. So I can't tell you whether string theory will be falsified 20 years from now. There would have to be 20 years of history that would tell us whether or not that's going to be true. But, you know, people worry that if we're talking about such small length scales and quantum gravity and the interior of black holes and the Big Bang, which we can't really recreate in the lab, how can we be sure that what we're doing is actually science? And, you know, I think the best answer to that is that in physics we can't always directly measure what we would like to study. Sometimes we have to go about it indirectly. I'll give you a small example. In particle physics, it's thought that protons might not be stable. They might eventually decay, that diamonds are not forever. But what we've learned is that the lifetime of the proton is actually longer than the lifetime of the universe. It's a very long time, 10 to the 36 years or something like that. And how have we learned that the proton does or doesn't decay? That involves a very high energy process, the decay of the proton, which we can't see, even in the Large Hadron Collider. But what we can do is something clever, is instead of taking one proton and waiting for an inordinate number of years for it to decay, that would take many PhD students. Instead, we say, what I'll do is I'll take a huge number of protons and hope that in a year, one of them does decay. And how many of them decay will tell us how rare that process is, and the rarity of that process gives you an indirect window into that process that you can't directly measure. So I'd say that's the spirit in which string theory is offered, is a tool to be able to ask the sorts of questions that we want to ask. But absolutely, it could be overturned tomorrow. A set of superior tools could come along and wipe the floor with string theory and say, aha, you have to learn our tools now because you have been superseded. It could be that people could invent gravity 4.0 tomorrow that would have many features that would render string theory a bit obsolete.
Good. Why don't we go in studio?
That was a great talk. I could listen to you talk forever. This is great. I have a random question just off the top of my head.
But it's written down.
Not planned at all. Okay, so I recently read this paper called The Holographic Turbulence by Adams, Chesler, and Hugh. I don't know if you're familiar with that paper. It uses the well-known mathematical duality between fluid dynamics and gravity to model fractal behavior.
This is called the fluid gravity
the
correspondence.
Fluid gravity.
And it uses this idea of the world as a hologram.
They're connected. And so I was just wondering what the connection is, or do you believe there's a connection between black holes and the holographic principle and fractals? Fractals are near and dear to my heart, and so I really want to try to fit that into the equation.
Yeah, well, we know that black holes and the holographic principle are sort of intertwined. They're sort of all cuddled up in one cuddle pile. They're really together in terms of the way they think about the universe. As far as fractals are concerned, they can arise in a very broad set of contexts, in mathematics or formation of certain things in nature and beautiful patterns that we see. And there are phenomena within string theory that show chaotic behavior or turbulent behavior or fractal behavior. And the beauty of the hologram tool set is that it allows you to sometimes study in what would be a complicated process in the CFT, you can study it using an uncomplicated process in gravity. So gravity allows you to have a tool to interrogate the CFT and be able to do things that people weren't previously able to do. So I can't say for sure that those concepts are joined at the hip, but I do know that chaotic behavior and fractals can arise in the context of the theories that describe our holograms. So absolutely, and nonlinear physics, which gives rise to fractals, is also relevant to what happens around black holes. There are lovely phenomena called the attractor mechanism, for example, that are very beautiful aspects of dynamical systems that arise just in the context of black holes. So mathematically and physically speaking, black holes are an immensely rich area of investigation. And, by the way, one of the reasons to do string theory is it's cheap. We don't actually require any experimental equipment. All we need is pencils and paper and erasers. We're not that great. And computers, because computers help us do symbolic algebra as well as numerical stuff if we have to do numerical simulations to crack some of these puzzles associated with black holes. But that was a very beautiful question. I'm sorry I couldn't get into a greater level of detail, but if we have a little huddle afterwards, you'd be welcome to ask some further questions then.
Let's take a question from the in-studio audience, and this will be our last question, and then we'll let the online audience know they're going to be online for an extra 30 minutes, so don't hesitate to ask more questions there. And if there are in questions, and Aidan, if you have more questions, we'll huddle after we say goodbye to the online audience. Okay, please, go ahead.
So if a black hole loses information, well, I've heard a theory that there was an opposite of a black hole, a white hole, where things then go in, it's the opposite, it's sort of the opposite, it sends things expanding.
Yes.
Would that therefore gain information to make up for the loss of information?
Wow, that is a
hole?
fantastically sophisticated question. Are you sure you're not a PhD student? could you just repeat the question? Sorry, I'm so tired that I have forgotten the essential point that you were making. My apologies.
So if the black hole loses information...
Oh yes, you were asking whether white holes can restore information.
Yeah.
So the essential property of a white hole is instead of having a black hole singularity in the future, it has a white hole singularity in the past. So what that means is that there's a past event horizon and things can pop out of it. And white holes are a mathematical solution to the equations of the fabric of space-time. But I want to warn you that they don't necessarily have a physical interpretation like black holes do. And the reason is something discovered by Doug Erdley and another guy whose name I've temporarily forgotten, which is very embarrassing. But 20 or 30 years ago, they discovered that if you take a white hole, which is a bona fide mathematical solution to Einstein's equations, and you try to poke it just a little bit, as I said, physicists like to find interesting systems, poke them and see what happens, what you discover is that the white hole is actually a fundamentally very unstable object. And it can't just stay there according to the mathematical equations. If you poke it even just with one subatomic particle, it becomes very unstable and it actually will collapse and form a black hole instead. So that fact, which doesn't even require string theory to show, they managed to show that just using the equations of general relativity and some aspects of perturbation theory. And they were able to show that white holes are probably not physical objects that are relevant to questions like throwing things and using graduate students to do measurements. So most likely, white holes with their funny singularities and past event horizons out of which things can pop, as you say, decreasing the entropy, which would seem to violate your sense of the second law. The problem is that those objects are just really unstable. They're sort of a figment of a mathematical imagination. They're not really physical. And the way we tell is to say, well, that there is a very beautiful mathematical solution of Einstein's equations, but if I poke it a little bit, what do I find? Is it a reasonable object? And the answer is sometimes we can find mathematical solutions of Einstein's equations that turn out not to have a physics interpretation. Another example that was discovered by Professor Rob Myers and Gary Horowitz, who's a well-known physicist at UC Santa Barbara. Rob Myers is one of Canada's premier gravitational string theorists. He's more famous than I am, actually. But Horowitz and Myers said, well, another solution of Einstein's equations that you can have mathematically is a negative mass black hole. Now, I know that sounds a bit bonkers to have a negative mass, but people are imaginative and people studying gravity are super imaginative. And so they wondered if it was an object that has a physical relevance. And they gave some sophisticated physics arguments to show that such an object doesn't really make sense in the quantum theory. That although it's a well-organized and well-defined solution of Einstein's equations at the classical level, before you include quantum physics, once you include quantum physics, the thing doesn't make sense anymore. So it actually doesn't have a physical interpretation, that negative mass black hole. And I would like you to think about white hole singularities in a similar way. But I may be wrong about this point, and maybe 10 years from now you'll prove me wrong by writing the paper. So that was a super sophisticated question. Thank you so much for that.
Ladies and gentlemen, Dr. Amanda Peet.